Hey, y'all, it's your soft-spoken scientist. Today we're going to work on our general chemistry lab 2, focusing on accuracy, precision, and percent errors, and I'll explain why each answer makes sense. Lab 2 is about understanding how good your data is, not just getting a number. You're learning how to judge results like a scientist. Okay. Accuracy versus precision. Accuracy means how close a value is to the accepted value. Precision is how close repeated measurements are to each other. So essentially, accuracy asks, am I close to the truth? Precision asks, am I consistent? Let's try this out on a practice problem. A student measures the mass of a sample 3 times, 10.01 grams, 10.02 grams, 10.00 grams. The accepted value is 11 grams. Is the data accurate, precise, or both? So the values are very close to each other, right? 10, they're all 10s, 01, 0, 01, 02, right? So they are precise, but they are far from the accepted value, so they're not accurate. So I would just say the answer is precise. That's a good question too. Measurements, 8.9 grams, 11.1 grams, 10.8 grams. The accepted value is 10 grams. This is accurate, precise, or both. So I see that the values are really scattered, right? We go from the range of 8 point something all the way up to 11. Because of that, it is not precise. No way, no how, right? But they average near the accepted value, specifically this value. So yeah, you could say accurate. Let's look at part 2, types of error. Random error affects precision. Systematic, that always is a doozy to say. Systematic error, try saying that 5 times, affects accuracy. So random error makes results scattered. Systematic error shifts everything in the same direction. Let's apply that to a problem. A balance is incorrectly calibrated. Calibrated is a big fancy word for saying start the machine. And always reads to weigh things, and always reads 0.50 grams too high. What type of error is this? Every measurement is shifted the same way. So accuracy is affected. So as a result of that, this is a systematic error. All right. So look at that, I wrote it twice. You know it now, systematic error. Because again, it's shifted, every measurement got shifted the same way, right? So let's take a look at this formula. The percent error is the absolute value of experimental minus the accepted divided by accepted times 100. You don't even need to put that there if you want to. Okay, percent error tells you how far off your result is compared to the accepted value. So using this formula, let's take a look at the practice problem. So the experimental density is 1.32 grams per milliliter. The accepted density is 1.50 grams per milliliter. Find the percent error. So again, that would be experimental minus accepted under the absolute value. So 1.32 minus 1.50 is negative 0.18. But because we're under an absolute value, everything must become positive, so it's 0.18, right? So we got 0.18. And another way you can think of it is 32 plus 18 gets you 50. Or you could just do 50 minus 32. A lot of different ways to play with the sign. You know you want to have a positive answer, but there's different ways of approaching it in your head. So that's that. So we have 0.18. We did subtraction. Let's divide by the accepted density, which is 1.50, right? So 0.18 divided by 1.50 is 0.12. I'm going to multiply this by 100 because that's a part of the formula, and I'm going to get 12%. And if you don't know how to do it, just move your decimal point twice, boop, boop, and you get 12%. A 12% error means the experimental value is reasonably close but not perfect. Okay? In lab reports, you're expected to explain error, not just calculate it. So you better have a good explanation. Let's try question 5. A measured density is lower than the accepted value. Give one realistic reason. Why? Well, you could think of it and say, oh, I don't know, the measured density may be lower, and this is always a great explanation for the discrepancy, due to trapped air bubbles, because that would increase volume in the instrument without increasing mass. This shows you understand the experiment, not just the math of it. Let's move on to part 5. And this is just written fancier for you guys, in case my handwriting's too bad. Part 5. So, most students lose points in Lab 2 by mixing up accuracy and precision, forgetting absolute value and percent error, giving vague explanations, blaming human error. That is how you tick a professor off, without specifics. Let's go on to question 6, a realism check. Is a percent error of 0% realistic in an experiment? Can everything in a lab go perfect? No. All measurements have uncertainty. So you have uncertainty. That's one thing. And a 0% error usually means it's either a coincidence or you accidentally overrounded. Either way, it's not right. If you understand accuracy, precision, and error, you're thinking like a chemist, not just doing calculations. I definitely have more videos coming out. It means the world to me. If you guys like this video, please subscribe. I got more videos coming out that are going to be lecture-based, but also lab-based. So stay tuned. This time is for everybody, especially you.